looking at ratcheting behaviour of welds in premium rail, particularly flashbutt welds. Just to acknowledge my co-authors, Chung, Darrien, Welsby and Wenyi. Two of them are here, so if you ask any tricky questions, I can always ask my co-authors. Just a bit of background to this work. This was sort of experience in heavy haul systems in the Pilbara region of Western Australia, where they're using a lot of premium rails. This is the sort of behaviour that
so keep it on. Yeah. No problem.
Is seen in some of the high traction curves where the locomotives are operating at maximum adhesion, up around 25, 30, or maybe even 40% adhesion, getting this localised cracking at the heat affected zones of the flashbutt welds. Some of the observations in the field were there's a bit of variation between welds in different rail grades, and we're talking about rail grades that are typically around 400 per mil. Obviously, they also vary a little bit with flashbutt welding conditions, depending on the width of the softened zone. The concern with them, first of all, is that if the cracks get too deep, of course, there's a risk of broken rails, potential impact on headwear limits, but also in terms of just getting the maximum performance out of the rails. So you find that it's actually the weld that's can compromise the performance of the rail. So what we decided to do was initiate a small project, just trying to get a better handle on predicting the damage at the welds. And there's quite a bit of work other people are doing in looking at localised damage at welds. Most of it seems to be directed at plastic deformation and wear, and not necessarily rolling contact fatigue, which is something that we're particularly focused on here. So just some of the things our options for assessing or alleviating the damage. I guess by reference to the typical longitudinal hardness variation in a flashbutt weld shown there on the right, you can try and do something to make the softened zone a bit narrower. There's a few options there, both in terms of the welding conditions and the rail grades. There's some other factors that need to be considered if you're trying to make narrower flashbutt welds. And the other one is to obviously modify the wheel rail contact conditions, and there's a couple of options there. One is obviously lower the contact stress levels at the gauge corner, or modify the creep conditions by putting in friction conditions at the gauge corner. These systems don't use any lubrication in those curves. There's a number of reasons for that. Historically, gauge face lubrication hasn't been particularly effective in those sort of operations because of the remoteness of it. And also, there's a reluctance to put anything on the rail that's going to compromise the available adhesion with them. If you're hauling a train that's about 50,000 tonne up a hill. So I guess two of the questions that come out of this were, well, if we're going to make the heat affected zones narrower, how narrow do they need to be to minimise the damage? And that's obviously the way we would like to go. One of the reasons for the concern about trying to make narrower welds is that the residual stresses in the welds will typically go up. So there's a risk of some pretty nasty fatigue failures in flashbutt welds if your residual stresses go up. I guess the question that's probably more relevant to this audience is really, are our damage prediction models for rolling contact fatigue adequate for the stuff they've got in welds? Because welds do have quite a range of microstructures. So this is illustrated here. This is a hardness distribution along a flashbutt weld in a 1% carbon hypereutectoid rail. So over here on the side is the perlite in the parent rail. Over on the far right is what you've got in the centre of the weld, or near the bond line. So typically very similar pearlitic microstructures. As you move away from the bond line, you see the perlites or the cementite is starting to spheroidise. This is a 1% carbon grade, so you can see evidence of the heavier cementite might form around the grain boundaries. And then you've got this animal here in the softened zone, which really has not much there to pin the dislocations when you start plastically deforming it. And while if you start playing around with the hardness distribution, you may not change that lowest point, but what you might change is the distribution over the rest of the microstructure. Just to illustrate the effect of that hardness or microstructure variation on the deformation behaviour, this is just some tensile results for two representative microstructures. This is actually in a domestically produced, Australian domestically produced heat-treated rail that actually has a softened zone in the middle of the head. So on the top is the microstructure for close to the gauge corner of the rail, paralytic microstructure, and you can see that the stress strain behaviours as you'd expect for a paralytic rail steel. But if you go into the softened zone, it's quite a noticeable change. You actually get a yield point elongation. Yield strength's much lower, the ductility is much higher, perhaps less evidence of work hardening. So the material in the softened zone is just not going to behave the same way if you're trying to predict ratcheting behaviour. So what we're trying to do, I guess, in the three elements of this particular project, the first element was really characterising the damage in some typical welds that have come out of track, and that was the stuff that we presented at Colorado Springs. The paper is referenced in the conference paper here. Second one is experimentally looking at the ratcheting behaviour of the material in the weld. That's actually being done by a postgraduate student who's about to go off to Southwest Jiatong University and do a lot of ratcheting tests. And the third element, which is what we're doing at the moment, is just looking at the modelling process to predict the cumulative plastic deformation. And I'll just illustrate where it's very preliminary stages, and I'll just illustrate the approach that we've taken. So the preliminary assumptions were that the material model would be similar to that of the parent rail, which is obviously grossly inadequate, but it was really to set something up so we could look then at the sensitivity to the heat affected width of the softened zone. We had ratcheting parameters for 3 heat-treated rail grades from the previous work, and so that was used to try and estimate some ratcheting behaviour for the material in the softened zone, based on the typical hardness distributions measured in welds that had come out of service. So this was the assumed hardness distribution in the FLASHBUTT welds in the three different rail grades with variation in heat affected zone width. This is just illustrating the modelling approach. Pretty straightforward, a fine mesh in the softened zone. One of the things we did initially was have both softened zones in the weld, so a full weld, but then to reduce the computational requirements, the later modelling was done with just one half of the weld and one softened zone. The loading conditions were 35 tonne. Typically these systems operate 35 to 40 tonne, friction coefficient of 0.4 and traction coefficient of 0.5, so fairly high slip or high traction type wheel rail contact conditions. This typical result, so this is the peak ratcheting strain after 30 cycles for the softened zones in those 3 rail grades at a 12mm wide heat affected zone. So you can see that there is quite a bit of difference between the 2 rail grades, the lower carbon one having the higher ratcheting strains. If we look then at the results for which are in detail in the paper for the width of the softened zone, as you'd expect, you reduce the width of the softened zone, the strain amount of strain after 30 cycles drops right off. There is, again, a bit of a difference between the 3 rail grades, with the low alloy one perhaps having the highest sensitivity to the width of the softened zone. The last one graph shows the width of the strain rate, similar trend with the strain rate. So that's the extent of the work we've done to date with the modelling. So it's a very preliminary look at the width of the softened zone. There's obviously a lot of extra work that needs to be done to incorporate the ratcheting parameters. There's a couple of other considerations that need to be factored in. With a weld, of course, you're going to get a change in the surface geometry as it deforms. So your loading conditions, you've got to build in some ability to the increase in the dynamic load that's going to come with that, which makes it computationally even more challenging. So at this stage, we sort of concentrated on setting it up so we could look at the width of the softened zone. But the next stage will be, once we get the ratcheting parameters for the material, we will then be able to extend the analysis. As I said, this was basically the focus of the ongoing work. It probably will no doubt have an update at the next conference, and probably a second paper to do with the actual ratcheting stuff, measurements that have been done. I think that's it. Thank you.